This invitation to this conference. It's a pleasure to be here in IMPA. I didn't know IMPA, so it's a good, very good place. So what I want to talk about actually is the Laplace equation plus a f function of u less than equal than 0, that means supersolution, in Rn minus a fixed ball. And find f should be from 0 and with f of 0 equals 0. So a positive nonlinearity with the unique 0 at 0. And find somehow the optimal condition on f, a general f, to have existent or non-existent of solution of that equation. But let me start with reviewing some known things about. There is many things known about that equation. I will give a little review, classical review of standard things. So if you consider problem in all Rn with the power nonlinearity and p is positive, well, of course there is a difference between n equal to 2 or n bigger than 3, the dimension, where of course if the classical Gidas-Proc theorem says that for p less, for inequality here in all Rn, if p is less than this critical number, then there is no solution. There is also a proof by Chen and Li. That's more or less classical. And then in exterior domain, there is a result by Veron, which says that in an exterior domain, as the same result, I mean, that there is another critical exponent for supersolution or solution even. If p is less than this number, there is no solution, or the only solution is the trivial one. And also in all Rn, at the same year, in the 80s, Gidas proved that in all Rn there is no positive or non-negative supersolution, or all non-negative supersolution are trivial, if p is less than this number. So, of course, this for the power nonlinearity, these results are optimal. For p bigger than this number, you can find solution in all Rn, and if p is bigger than this number, you have singular solution, so solution there, super solution, so our solution is, of course, in this domain. So the singular solution is a solution also in the complement of a ball. And then there is many things done in that direction, putting a more general operator. What does it mean? The first things to mention is that for a given operator, if it's radially symmetric, I will suppose here radially symmetric, then I will make some comments. There is a function with a power function that I call fundamental solution. So there is a power, exact power. Here I'm switching to more general operator. It can be a fractional operator or whatever. But it can also be the Laplacian. But this is the same as Gidas result when it's the Laplacian. You have an operator where I have a fundamental solution, and then you can exactly repeat somehow the Gidas result. What does it mean? This equation does not have solution in all Rn. If p and the result is optimal. if p is less than this number. So you just replace the dimension by the dimension introduced by the fundamental solution. And you have somehow here a more general operator, and you can prove that. So in particular, as an example, you can consider the fractional Laplacian, and you can prove that there is no solution of that in all Rn if p is less than n over n minus 2 alpha. And of course, if p is bigger than this number, there are solutions to that equation. Let me talk a little bit about fundamental solution, because it's nice to see. I will throw a picture what I mean for fundamental solution for a fractional, and then I will maybe start with the classical fundamental solution for the Laplacian. So you want to find solution to that equation with a power function. So, or maybe you consider a more general operator, which is the Pucci operator. I will write it like this in a radial version, because you want to find radial solution. So in a radial version, you can write the Pucci operator as alpha times the second derivative times beta n minus 1 in radial coordinates u prime. And you want to solve this to be 0 for radial solution. And then you plug in a solution like this, which is a power. I will just throw a picture because there is a chain saying I want to be all the fundamental solution in the same class. So the first thing is with a negative power, so it's this singular solution, which corresponds to R to the minus sigma with sigma positive. And then it's the log, minus log, and then this another type of with sigma negative. So that's it's written the other way around, so it's with the plus here because it's negative there. So it's like this. And sigma negative here. Here, so this is negative and sigma is positive. So in this class, I want to compute, let's say, the Laplacian, which is the same when I take this set to be both the same, and I compute, of course, with a power. So I compute this for a power, and then the first derivative, of course, is alpha times r to the alpha minus 1. The second derivative is alpha minus 1, r to the alpha minus 2. And then I plug in that here, and I notice that, for example, if I'm looking for sigma there, alpha here, but if I plug in this optimal condition, since I'm in this class, this is convex function, decreasing function. So if I compute the Pucci, what's called the Pucci operator of U, then what I get out here, since this is concave, I need to be, so the equation is a big lambda times the second derivative because of that, plus little lambda times the first equal to 0. Because this is decreasing, I want to maximize, so I put the smallest that I can here and the biggest I can here, because this is positive and this is negative in what I'm assuming with it. Maybe there is a change of sign here because here is a minus, but I want to come into that in a minute. So if I compute this, maybe I throw it in the other part of the blackboard. What I get very easily is that I will divide it by little lambda. So what I get is alpha factor times little lambda n minus 1. What the of course, some factor, r to the alpha minus 2, which has a common factor because I'm dividing by r here. So the first derivative, this factor out in both. So here I have plus alpha minus 1. That's, of course, the Pucci of u in this case. So as you see, you can say that this is alpha. I will call this n minus 1 tilde, and then n minus 1 minus 2 plus alpha, r to the alpha minus 2. So this is what I call C of alpha, r to the alpha. And I want to be that this function has a 0. And that's the fundamental solution. And so I take alpha be this exponent. So what I want to throw a picture of this function. This is a quadratic function and has 1, 0. What happens? So the standard thing is that you have, this is the fundamental solution. Here is minus n plus 2 alpha to like this. Or maybe it then, when n is equal to 2, it has 2. I mean, it's just a quadratic. It becomes like this, of course. And then you have also this possibility also, depending on this guy, if it's bigger or less than 2. So in general, for a general operator, you can more or less do the same. So if I compute for a general operator, radially symmetric operator, if you compute f of this, you get some constant, even integral operator or whatever, you get a constant times some factor, sigma minus 2 alpha. Right? And so what we can prove with this joint work with Patricio Fellmer in Chile is that we can find a sigma where this vanishes. Here is f, sorry, this I changed notation, this is f here. So it's just to find a 0 of that function, right? So it's just find a 0 of that function. And then I call the dimension this number minus plus 2 alpha. So it's just the same thing here. And I want to mention before going how to prove exactly that this C function has 1, 0. A 0 is 0 all the time, but you want to prove that there exists another 0. I want to mention that there is many people working on that. It started with Labutin in 2000, then Curileoni used that, Calpuccio Dolcetta, Fellmer, also Armstrong, Siriakov, and Smart also proved for non-radially symmetric operator, second order, they proved that there exists a fundamental solution making degree theory in the spheres, because when it's not radially symmetric, you can factor out this. So there is a very nice work by Armstrong, Siriakov, and Smart, where they prove for more general, no radially symmetric here, just talking about radially symmetric operators, but for general operator, you can find fundamental solution. But let me finish more or less the proof, because somehow with a change of sign, this quadratic function, because I'm changing sign, looks like this. So somehow for here I'm drawing the picture for integral operators, and the integral operators, if n is too big, somehow this C, what I have before, this C function here becomes a singular integral, so it diverges here and here to minus infinity and so on. So I have this picture, and here I have a fundamental solution because I have a 0. Here I have a 0, and here what I will do here, that's the problem. Somehow here is the situation where I don't have 0, the log should become out. Because when you don't have fundamental solution, Exactly. Then when n tilde here is 2, then you don't have, is this picture, right? And you don't have fundamental solution, so the log should become out here. How did it come out? But, well, the thing is what I prove here for fractional things, it's what I was telling, but I proved that also some qualitative properties that it has only 1 0, at most 1. So this means there is a unique, somehow in this class, a unique fundamental solution. So, and what happens if I have this case, not 0 at all, then the log should come out, and then you see that from one-sided, because you have one sign here, the other sign here, somehow the power here, since you have one side and the other sign here, you have sup and super solution, which converge, which is the power, just the power that converges to the log. And are sup and super solution, and then of course that's the proof. And so if you don't have 0, then you find somehow by sup and super solution the log. That's the more or less the idea behind the fundamental solution and this Gidas type result. I will end up with that. I don't want to generalize now, coming back to the first equation. So I want to come back with the Laplacian, but now not generalize the operator. Look for more general nonlinearities. What's the main thing of this talk? So I want to focus in what is the more general nonlinearity that I put there so that I have still the Liouville type theorem. And this a work starting by Armstrong and Boyan, which tell you a little bit further. I find it nice because it's just that what they prove, or more other things that I want to mention next. But for the Laplacian, they prove that if you have a positive nonlinearity, it's just what matters is just a condition on 0. Only a condition on 0. So just with the right power, at 0 the limit should be positive. And that's what they prove, and actually they can generalize to fully nonlinear, P-Laplacian, and these kind of things. But the key point is just you need to impose some condition. So the nonlinearity, F, can do whatever they want, and here just a power behavior somehow, near the origin. So I want to, the main thing of this talk is, can I generalize this? For example, for a log perturbation, what can I say? What's the more general F that I can put? And the thing is to find an optimal condition. So actually, in the same paper, they prove that, of course, if this limit is, this lim sup is less than infinity and p is bigger than the critical exponent, then this function, the singular solution, is you can construct a solution of the problem. It's not hard. But of course, what I want to mention is that, of course, these two conditions are not optimal. And I want to catch somehow the optimal condition. That's the thing. And here, the example not treated, it's, yeah, you can, oh, sorry, I put 2 thetas here. It's just 1 theta here. Just a misprint. What happened with this example for theta positive, which is not considered in the literature? So erase this theta here. So it's a log perturbation. Of course, you can think about other perturbation, but this is the more natural because you can somehow do computation in our condition. So, of course, there is an analog. I don't, in dimension 2, because it changed, the fundamental solutions changed. So the condition, since you have a log, the condition it's not exponential condition, it's a Sorry, it's an exponential condition, not a power condition, because the change of the fundamental solution, which is the log. And they also prove this result here. So it's more or less the same result that I mentioned, but in dimension 2, there is analog of that. Of course, this result is not optimal too. So that's the main, as I mentioned, that's the main thing is what condition, what can we give to that problem so that we have solution or not. And this actually is the joint work with Alarcón and García Melián, some guy of Spain, Tenerife, La Laguna, and the other guy for my university. And what we prove is that for this equation in Rn, there is an optimal condition which says that if this integral is finite, then we have a solution, and if this is infinite, then we don't have solution. Of course, in the power case, this means that because you make a change of variable, and this means for this example, this means for theta less than 1, that we have non-existence, or for theta bigger than 1, we have existence. So that's the. And of course, there is analog in dimension 2, which is more or less the same, but you need to replace here somehow for every alpha some, and becomes a condition in infinity. The difference between dimension 2 is that they become a condition at infinity. I didn't mention that before, but it's very relevant, because here the previous thing is a condition at 0, and for the exponential things, it's somehow reverse things. So it's a condition at infinity, but the same time of result holds. Optimal condition in dimension 2 to have existing or not with our general F. So what's the idea of the proof? So very quick review of the ideas of the proof. So the first thing is that since you are in a complement of a ball, somehow the existence of supersolution, which is very strong because you are in a complement of a ball. I will make a remark after that. But if you are in a complement of a ball, you can reduce the problem to a radially symmetric solution. If you have a supersolution, you can construct very easily a solution, a true solution. You can construct just by a supersolution method. And it's radially symmetric, because it's a minimal solution, and you construct it in annulus, and then you take the limit, so it becomes a radially symmetric solution. So that's, and then you make the change of variable, a change of variable, which is related, of course, with the fundamental solution, and since here you reduce the problem to an ODE, then you can reduce it to an ODE with a white here, performing this change of variable with the fundamental solution. Yeah, it seems to be a very naive two second order ODE, but this white somehow caused some trouble to analyze really in details this equation. So, and what we have is that this number is bigger than 2 by condition on n. I'm just in the case n bigger than 3. I don't want to mention anything about the case n equal to 2. So the thing is, what can we can say about existence or non-existence of that funny looking problem? I mean, very, very.
Alex, at this stage you just need a local solution.
Local, yes, local solution. Yes, local solution gives me solution to the other problem, maybe with a not that big R, but but local solution are, for that, it's equivalent to the other problem. So I changed somehow infinity to 0. That's some sort of Kelvin transform V1. And the thing is that under this condition, you can prove actually using, there is some work on the, I find some reference in the literature, there are in my paper, but for existence, but was not optimal for that problem or not that general that what I find here, but the method what we use is be carefully with a fixed point argument at the end. I mean, making the good estimate with this condition really to show the fixed point argument works. That's the existence part, and the non-existence part is somehow I find it very nice because you want to estimate, and this is the problem that this ODE is not integrable. That's the problem and then somehow you estimate once, and then you plug it in the equation and iterate that a lot of times, infinitely many times actually, and you find the contradiction. And of course, when you iterate, you need to somehow control the constant, and of course there is a geometric series appearing like always, which needs to converge, and then we get it. So that's the idea behind when this is infinite. It's just you integrate the equation, begin with the first estimate, and then you iterate the estimation, and then you refine the estimate to get that it's impossible to have solution with that being infinity. So that's the idea of the proof, nothing else. So I want to mention some generalization that we can think about. You can put whites, and it works. It doesn't change too much. You can put gradient terms. You can think about fully nonlinear. Of course, and the same, here I mentioned that the same time of result, you need to change. For example, if you put Pucci operator, you need to change n by n minus or n plus. Yeah, n minus, n plus, this is n minus with this n minus with this notation, and n plus is the rarest one. You need to be careful about what of this type are bigger than 2 or less than 2 and so on, but more or less the same type of result holds true for a general fully nonlinear radially symmetric operator. The assumption is that the operator is radially symmetric. Actually, I want to mention that there is an open problem. What about not radially symmetric operators here? But in general, you change the condition. I mean, the condition, coming back, this condition, what you change here, this n here change. The only thing that you reach out with the same equation, because you perform this with the fundamental solution of the equation, and then you just come here with different dimension there. That's the thing, depending on these two numbers. But I will just skip this. And of course, you have the same types result also for the P Laplacian. You can performance, and of course this appear here, this fundamental solution, which is the fundamental solution related to the Laplacian. Of course, when P is n, then you have these other type of things. And of course, there are three different features here. But that's the rest. So some remarks that I want to make. The first one is that in Rn, existence of supersolution implies existence of solution, actually radially symmetric solution. That's the proof. And in Rn, this is false. That's what a main difference in Rn. This is false. This is not true in Rn. Supersolution are very different of solution in all Rn. Yeah. So in complement of a ball, it's a very different story somehow. What is this? I don't know. It's just something strange appear here, but no, the thing is that just to have in mind, related to what I mentioned as a remark, I can erase everything here. So let's come back to this equation, just to think about this equation. In Rn, the set for non-existence is open in the parameter, in all Rn. But in the half space, or sorry, not in the half space, in the complement of above, the range of non-existence is closed. So it's a really different story, all Rn, and the because of course here I want to mention that the generalization that I'm talking about for this case, I mean in the fully nonlinear setting here was also, and some others, was also done by Boyan and Armstrong with the other condition, not the integral ones. So it's just one step further, if you want. The log perturbation at the end, or as an example. So, sorry. So I want to end up with some open problems that I'm thinking on. So what's integral condition for fraction and Laplacian, for example? Should be an integral condition for fraction and Laplacian? I think so. It should be just replace this by the dimension by, I mean the 2 by 2 alpha. That's told. But open. Not radially symmetric fully nonlinear operator. What you can say? Can you really do the method work? That's one question. Integral condition for the half space. For the half space, actually, Boyan has a very nice result also with Armstrong, which says that two conditions plays into the game. Not only a condition on 0. In the half space, you have condition at 0 and at infinity. Two conditions. But can you really think about integral condition in that for the half space? That's an open problem. And here is something that I always like to mention, which is for my thesis. It is a nice open problem. So Pucci operator with an equation in R without radial symmetry. Just I will come back to the Pucci operator. So the conjecture, actually, which is false, is that the same result that I mentioned here should be worked replacing this number here by this number here, the dimension. That's the conjecture. It's exactly the Gidas-Prague result. Should be this holds true. Just replacing this because the fundamental solution. And what I prove in my thesis actually is that this is false. Actually, this is false, so it's more delicate. As I said, the problem in all Rn, it's more delicate. And actually, there is a critical exponent only in radial symmetric situation. There is a critical exponent, but it's slightly smaller than this number. So it's really the fully nonlinear setting somehow destroyed that this number is a critical exponent in all Rn. So that's a nice thing.
For the complement of a ball?
No, but in the complement of the ball, the critical exponent, sorry, there are two critical exponents. This is the critical exponent in a complement of a ball. And the other is bigger. You have a 2 there. Right? So, and this result was my thesis. Proof exactly that there is no solution and therefore P bigger, but just in a radial symmetric situation. And what's open is the no radial solution. Not radial symmetric solution is completely open. When I heard Javier talking about the two radially symmetric, maybe there is something to think about. I was wondering of that. Because maybe with only two, splitting two radially symmetrics, maybe you can say something. So thank you for your attention.